This hit and run is on GLS for autocorrelation. In fact, we might say 2 cheers for generalized least squares. Generalized least squares involves this procedure. You transform the offending equation into one that obeys the Gauss-Markov assumptions and then use ordinary least squares. And then you get all the desirable properties of that ordinary least squares estimator there. You know, it's a best linear unbiased estimator. Hey, what could be better? Hey, and why did I say 2 cheers? Isn't that supposed to be like 3 cheers in the old British Navy movies? Hip, hip, hooray, and all that? Well, I'm going to show you why. We do have some reservations about it, but it is a very neat piece of mathematics. So let's start with the simplest equation we can think of that might have an autocorrelated error. Yt is equal to beta 0 plus beta 1 times x in time t, there it is, plus epsilon t, and our simplest model would have the error term look like this, that epsilon t is equal to, let's see, there's last period's error term, but it's got this row in front of it because a little piece of last period's error term gets carried over into this period's error term. And then there's also a ut on the end, where ut is one of those nice classical error terms that obeys all the Gauss-Markov assumptions. So what we've got is a defect in the error term, but a very clean one, in that it's just equal to rho times the last period's error term plus this nice clean error term. And now, just a little bit of algebra. Do you think you could solve that equation for ut? Oh, sure, that would be easy. Because if you just subtract rho times epsilon in time t minus 1, just subtract that term from both sides, then it goes away, leaves ut all by itself, and then leaves you with epsilon t minus rho times epsilon in time t minus 1. Hang on to that result because we'll use it here in a minute. Now, what happens if we lag and multiply? Okay, there we go. We're going to lag and multiply 1 by rho. And we could do that. Sure, that would just give us equation 2. So we're going to lag everything that's in equation 1 period, and then we're going to multiply everything through by rho, and so we're going to get another true equation. So when we lag that first term, it's y in time t minus 1. When we multiply by rho, just stick that rho there in front of it. And now for the constant term, pretty much the same thing. Rho times beta 0. The constant term does not have a t anywhere about it. That's why it's the constant term. Doesn't change over time. There it is. Rho times beta 0, so we don't have a t to lag there. And then beta 1 is going to be multiplied, there we go, by rho in time t minus 1, that value of x. So it's beta 1 times rho times x in time t minus 1. And then the error term of this equation, once again, here's our procedure. We lag at 1 period, epsilon in time t minus 1, multiply by rho. There we are. You can work it out on your own, and I think you'll see that what we did was just to lag that thing and then to multiply each term by rho. So we now have a true equation. But now, using that good old trick of subtracting equations, we can take a true equation, subtract a true equation from it, and what we get is, hey, a true equation. So the first term would be yt, and then we're going to subtract off the first term of this equation, minus rho times y in time t minus 1. That's going to be the left-hand side. That's the new dependent variable of the equation. Then next we're going to have beta 0 minus its counterpart there, which is rho times beta 0. And then we're going to have plus beta 1 times xt. Got to account for everything up there. So there's the thing that we've got to account for. And now we got to subtract off beta 1 times rho times x in time t minus 1. See, we're just doing all the subtraction. And then we've got the error term of this subtracted equation, which is equal to the epsilon t above there minus this rho times epsilon in time t minus 1. Okay, we are very close to something beautiful here. Ha! Let's see why. Look at this. Epsilon t minus rho times epsilon in time t minus 1. What do we know that that is equal to? Hey, look at that. It's ut. It's a nice, clean error term. So what that says is, if we just estimate this equation right here, it'll be an equation with a nice, clean error term. It will obey the Gauss-Markov assumptions, and our ordinary least squares estimates will be just fine. So let's just do a little notation here. The transformed equation we're going to estimate is going to be yt star, that's just a transformation of yt, equals beta 0 star, okay, plus beta 1, that's the thing we're always after. We want to know what's that beta 1, want a good estimate of that, times xt star plus ut, where these variables would have the following definitions. Yt star is equal to yt minus rho times y in time t minus 1. Beta 0 star is equal to beta 0 minus rho times beta 0. And xt star is equal to xt minus rho in time, that's x there, in time t minus 1. Notice how easy this is then. We just do a little transformation on the data there, the dependent and the independent variables. We run ordinary least squares on it, and we get these great estimates. Now, what could go wrong with this? You know, why did I just say 2 cheers? Why isn't it 3 cheers for using this technique to correct autocorrelation? Well, let me show you the problem here. We assumed that autocorrelation took on this nice, neat form, but it may not do it, and we never really know exactly what form the autocorrelation takes, because that depends on this rho, which is a population characteristic that we can never actually observe. No problem, you say? Let's just go estimate it. That would be rho hat, and rho hat might be a very good estimate of rho, but all the same, it is an estimate, and it's not the true rho hat. Further, in time series, we're often working with small sample sizes, and so we run out of degrees of freedom, we run out of statistical reliability when we're estimating a rho and sticking it in there. What this means is that, especially for the small time series samples we're often using, when we go in and estimate rho and actually plug in rho hat here, we're not totally sure that what we get is better than just running ordinary least squares. That's why it's 2 cheers instead of 3. So let's go have a look at the stupid list. Very important entry on the stupid list. If you have time series data, suspect autocorrelation. Yeah, of course, it's almost always going to be there, but understand that correcting it might not make your estimates better. And that is why we say those 2 cheers for GLS. That is a hit and run on GLS for autocorrelation.